This is Algebra 2 practice test number 6. All right, in number 1, we are just adding, or I should say we're combining like terms. We have a positive 6i and a negative 7i. Notice that I'm taking the sign in front of the term as well as the term itself. Those add up to a negative 1i. And then the only thing that's left over is this plus, or this minus 4. I'll put the minus 4 up front. To simplify, whenever I have a 1 in front, I'm going to call this thing a negative 4 minus I for my final answer. In number 2, my like terms, I'm going to first look for my real terms. I only have one real term, this plus 2, so I'll rewrite a positive 2. And then I have 3 imaginary terms. In this case, I have a negative 6i, a minus 3i, and a plus I. These we'll have a plus 1 in front of the I. The coefficient is 1. If I add these together, I have negative 9 here, and then I go in a different direction to negative 8. This is going to be minus 8i for my final answer, which I'll then box. In number 3, we have parentheses, which we have to deal with. This minus sign is being distributed, so I'm going to go ahead and say distribute the minus sign into each of these terms, making this a negative 8 minus a 4i. And now I can combine my like terms. Let's go ahead and start off with the reals. I have a negative 2. I have a negative 8. Those are all of the real terms. That adds up to a negative 10. Looking at all the imaginary terms, I have a plus 3i, a plus 8i, that's 11i so far, and then down 4i, so 11 minus 4 is 7. So this is going to be a total of plus 7i. Final answer, and box it. In number 4, we need to distribute. So this negative and the 5 and the I are all being distributed into these two terms. A negative 5 times a positive 3 is a negative 15. Don't forget the I. Negative 5i times a negative 7i. Negative times a negative is a positive. 5 times 7 is 35. I times I is I squared. We're not done yet. In order to simplify every problem in this unit, anytime you see an I squared, we switch this out for a negative 1. So this is really saying 35 times negative 1, which is a negative 35. Negative 35. And we typically write the real number first and this imaginary term second. So I'm going to say minus 15i for my final answer, and we'll box it. In number 5, we need to rewrite this. Whenever I have a power of 2, that means I'm multiplying this base by itself 2 times. So this is going to be 7 times, or sorry, it's going to be in parentheses 7 minus 7i times itself 7 minus 7i. I'm ready to distribute. 7 times 7 is 49. 7 times a negative 7i is a negative 49i. And then I'm taking this negative 7i, I'm including the sign in front of it. It is a very common mistake to ignore the sign in front of it. And I'm going to distribute that negative 7i into the plus 7i, and that's going to be another negative 49i. And again, distributing into the negative 7i, a negative times a negative is a positive. 7 times 7 is 49. I times I is I squared. Again, whenever we have an I squared, this is going to turn into a negative 1, which means I really have a negative 49 here. This negative 49 and this positive 49 will cross off, so I'm going to go ahead and show my work by crossing off each of those. And what's left over is this negative 49i and another negative 49i, which is really close to negative 50i and negative 50i, which would have added up to negative 100. We were off by a little bit. The final answer here should be negative 98i, which I'll then box. In number 6, we have a lot of distribution to do. So a common mistake is to think that this 2i is distributed to all 4 of these terms. That is incorrect. You either distribute it to the first 2 or the last 2. Most students here will do the first 2, so that's what I'll do as well. 2i times 5i, or 2i times 5 is 10i. And 2i times a negative 5i is a negative 10i squared. And I rewrite the rest of the problem. I still have this 3 minus 5i. I would like to simplify. Whenever I see an I squared, I can turn that into a negative 1. So this is really a negative 1 times a negative 10 for a positive 10. So it's a 10, and then I still have this plus 10i, and that's still being multiplied by 3 minus 5i. Now it's time to factor this, or not factor this out, but multiply this out again. So I'm going to do 10 times 3, which is going to be 30, 10 times negative 5i is negative 50i. A positive 10i times 3 is a positive 30i. And finally, a positive 10i times a negative 5i is a negative 50i squared. Again, anytime that I see an I squared, I automatically turn this into a negative 1. This is a negative 1 times a negative 50 for a positive 50. A positive 50 plus a 30 is an 80. And a negative 50i plus a 30i is a negative 20i. Negative 20i. That is my final answer. Notice that I'm always writing it with the real term up front, the imaginary term out behind. All right, and number 7. This one is testing our order of operations. So if you have forgotten your order of operations, you can go back to PEMDAS, or please excuse my dear Aunt Sally. Are there any parentheses? No. Are there any exponents? No. Is there any multiplication or division? There is no division, but there is multiplication. You can see that these two terms are trying to be multiplied first. So I'm first going to say 4 times negative 6 is negative 24. I times I is I squared. I still have a negative 2i out front, and then I can simplify this. Whenever I have an I squared, that turns into a negative 1. And this negative 1 is being multiplied by a negative 24 for a positive 24. I still have to bring down this minus 2i, and there are no more like terms to add or subtract, so I get my final answer, and I put my real term in the first spot and my imaginary term in my second spot. Number 8 is again testing our order of operations. In this case, I do have some parentheses. I cannot combine the like terms inside the parentheses, so I'm forced to move on to exponents. There are no exponents. There is multiplication happening. This 6 is being multiplied by this quantity. I can distribute that and say 6 times negative 2 is a negative 12, and 6 times a negative 5i is a negative 30i. I'm going to rewrite the rest of the problem, plus 7 times 5i, and then I can add and subtract like terms. So combining like terms, I have a negative 12 and a, oh wait, I need to, before addition and subtraction, there is another multiplication that I forgot. This multiplication problem right here needs to be solved first, or simplified first. 7 times 5i is a 35i. Rewriting the rest of the problem, I have a negative 12 and a minus 30i. This 35i is a positive 35i, so I'm going to put a plus sign in front of it. And then I'm looking for my like terms. This is an imaginary term. This is an imaginary term. Adding them together gives us a 5i, and I can rewrite our negative 12 out front, which is our real term. Because this is a positive 5i, I'll put a plus sign here, and there's my final answer. Again, it's given in a plus bi form, meaning we have a real and then imaginary part. In number 9, we're supposed to graph each of these. Remember that the real number is graphed on what used to be the x-axis, and the imaginary number is graphed on what used to be the y-axis. So I'm going to go left 3, and up 3 from the origin. So I'm going to go left 3, 1, 2, 3, and then up 3, 1, 2, 3, and I get my final answer. Again, graphing negative 2 minus 3i. This is saying go left 2 and go down 3. Left 2 from the origin, 1, 2, and then down 3, 1, 2, 3, and I get my final answer right here. Moving on to number 11, we're supposed to go backwards now, and it's giving us a problem. Notice in this case I've gone right 2, and then down, follow that 2, and I've gone down 1, 2, 3, 4, down 4, and whenever we're going up or down, that is on the imaginary axis, meaning I'm going down 4i, and I put those together to get 2 minus 4i. In number 12, I'm going right 3, 1, 2, 3, so that's going to be a positive 3, and I'm going up 1, 2, 3, 4 for a 4i. Putting those together gives me a 3 plus 4i. In number 13, we're supposed to find the absolute value of the complex number. Again, this is the distance from 0, and if you have forgotten, the general idea here is that I have a complex coordinate plane like up above, and I'm going right 6, 1, 2, 3, 4, 5, 6, and down 2, and I have this point that represents 6 minus 2i, and I have a line going from the 0, or the origin, to this line. It should be straight, and I'm asking what is the distance of this red line. And to find that distance, we are essentially making this into a right triangle to utilize our geometry, specifically using Pythagorean theorem, or a squared plus b squared is equal to c squared. We know that all distances are positive. We ignore negatives, we ignore i's. We say that this distance right here is 6, and this distance right here is, I'm going to move this out of the way, that distance right here is 2. Not -2, not -2i, it's just a distance of 2. Yes, in the shadow dimension, but that's okay. So those are my legs of my triangle. Those are what I'm going to be substituting in for a and b. I'm going to have 6 squared plus 2 squared is equal to this hypotenuse c squared. Multiply these out. 6 times 6 is 36. 2 times 2 is 4. That's equal to c squared. Therefore, 40 is equal to c squared. And to solve this, I square root both the left and the right. Whenever you square root, you should have a plus or minus. But again, because I'm looking for distance here, I can never have a negative distance. So I ignore the negative, and I just say it's going to be positive square root of 40 for my answer. This is not the final answer because I need to do a factor tree for the square root of 40. The square root of 40 is also known as the square root of 4 times the square root of 10. The square root of 10 doesn't have any perfect squares, and to prove that to you, I can say this is the square root of 2 times the square root of 5. None of these are perfect squares. However, the square root of 4 is a perfect square. I can cross this one off and say this one turns into 2. Multiplying these three pieces together gives me 2 square root of 10 for my final answer. In number 14, I'm doing the same thing. I used a graph last time, but this time I'm going to take my shortcut and simply plug into Pythagorean theorem. Again, Pythagorean theorem is a squared plus b squared is equal to c squared, where c is my answer. A is going to be 4 squared. B, again, I ignore the I ignore the negative, and I'm just pulling out the 4, and I'm leaving it here. 4 squared, and that's equal to c squared. If you know your special right triangles, you might notice that this is going to be a 45, 45, 90 because these two lengths match, and you can immediately jump to the answer of 4 square root of 2. If you don't know how to do that, I will show you the long way here. 4 squared is 16. 4 squared is 16. That's going to be equaling c squared. 16 plus 16 is 32, which is c squared. If I square root both sides to get rid of the square, no, you always have to do plus or minus, but you ignore the minus because it doesn't make sense to have negative distance. And my answer is the square root of 32, which doesn't quite match this number yet until I do a factor tree. The square root of 32 is the same thing as the square root of 16 times the square root of 2, which seems appropriate given the fact that I had 2 of these 16s, which this is literally saying 2 of the 16s. The square root of 16 will always turn into 4, and that gives us our final answer, 4 square root of 2, which we got from the very beginning using special right triangles from geometry. In number 15, we have some division going on. The easiest thing, there are a lot of ways to solve this problem, but the easiest way to solve this problem is just to purely focus on that I and get rid of the I. The way that I get rid of the I in the denominator is by multiplying by I. I can't just multiply the denominator by I, I also must multiply the numerator by I, and the numerator is now, okay, we have to be careful here. This negative, it can stay up front, but I'm going to choose to put it into the top. So this is really saying a negative 4 times I or a negative 4i. If you choose to leave the negative out front, that is still correct. You can either have the negative out front, up top, or down below, but you can't have it in a mixture of the two. You have to have it in one of those 3 spots. In the bottom, in the denominator, I have an I times an I, which is an I squared. This is 8I squared. Again, anytime you see an I squared in this unit, you switch it out to a negative 1. And this is now going to turn into negative 4i over negative 1 times 8 is a negative 8. And from here, I want to do some simplification. I can divide the top and bottom by a negative 4. Negative 4. Why negative? I prefer my fractions to be positive. And 4 divided by 4 is 1. So this is going to turn into a positive 1i or just I. And the denominator, negative 8 divided by negative 4 is a positive 2. Our final answer here is I over 2. In number 16, again, the way to get rid of an I in the denominator is to just multiply by I. If I multiply by I in the denominator, I also must multiply it in the numerator. Doing this gives us an I squared in the denominator, which will immediately turn into a negative 1, which means our denominator is a negative 1. And now we have to worry about the numerator. Distributing this I into these two terms gives me a negative I plus 10i squared. Again, I have another of these I squared terms, which turns into negative 1. And this is now saying negative 10 minus I, which I'll write out over here. Negative 10 minus I. Again, I can choose to put this negative wherever I please. I'm choosing to put it up into the top now, which means I really have a a negative in the top times this quantity of negative 10 minus I, and there's nothing in the denominator. This was originally over 1, but simplifying that just goes away. I now have to distribute this negative into each of these two terms. So negative times a negative 10 is a positive 10, and a negative times a negative I is a positive I for our final answer. In number 17, this is a little bit harder because I can't just multiply the numerator and denominator by I anymore, because this will have an I left over when I multiply it by the negative 6. Instead, what we're going to do is multiply by the complex conjugate, which is a fancy way of saying we're going to multiply by the same thing that the denominator is, negative 6 and a 6I, but instead of having a plus sign, we switch it. If we had a minus sign, we would switch it. Conjugate just means you switch the imaginary term. So the imaginary term is going to switch to a minus sign, and we're going to leave that copied in the numerator, a negative 6 minus a 6I. If everything is done correctly, we should be able to do a shortcut down here. Doing the shortcut is going to be 72. Let's see if I get my answer correct. I think at the very end, we're going to have 72 over here, and the shortcut again is if I have some sort of a plus bi in the denominator. To get the shortcut, I'm just doing a squared plus b squared, ignoring the I, ignoring the signs. None of the signs matter. You just square the first, square the last, and then add them together. 6 squared is 36, 6 squared is 36, 36 plus 36 is 72. Let's see if that's actually the case by multiplying this one out, and then we'll just use the shortcut in number 18. No matter what, the shortcut does not work in the numerator unless you get extremely lucky. All right, so here we go. I'm going to multiply a negative 6 times a negative 6, and I get a positive 36. I'm going to multiply a negative 6 times a negative 6i for a positive 36i. Multiplying a positive 6i times a negative 6 gives me a negative 36i. And multiplying a positive 6i times a negative 6i gives me a negative 36i squared. I should have changed to a different color, though. Let me change that back to a different color like this. Minus 36i squared. In the numerator, I also have to distribute. I have a 10i that's being distributed, using a different color, to a negative 6, which is a negative 60i, and multiplying a 10i times this negative 6i gives me a negative 60i squared. Notice we have a bunch of these I squared terms. This I squared term turns to negative 1. This I squared term turns to a negative 1, which means in the top I have a negative 1 times a negative 60 for a positive 60. And I have a negative 60i, which I'll just copy down, negative 60i. And in the denominator, watch what happens. I have a positive 36i and a negative 36i. These are opposites, they cancel out. And notice that a negative 1 times a negative 36 is a positive 36, and this is going to be 36 plus 36, which is 72, as I predicted in the shortcut. Notice in this problem, however, I can reduce because I can divide both the top and bottom by 12. So if I do that, I don't have enough room, so I'm just going to grab this, I'm going to copy, and I'm going to come down here, and I'm going to paste. I'm going to say that this number, if I divide the numerator and denominator by 12, 60 divided by 12 is 5. What happened to my I? I didn't get carried in my copy paste. And then that's going to be minus 5i. And then 72 divided by 12 is 6, and I get my final answer. In terms of checking the answer key, just be aware that I can always multiply both the numerator and denominator by a negative 1, which means the answer could also, in theory, be a negative 5 plus 5i all over a negative 6. That is also a valid answer. You do not need to put both of these. Either one is fine to get your full points. We are on to number 18, which is the last problem on this practice test. Again, we need to get rid of this I in the denominator. The way that we do that is multiplying by the complex conjugate, meaning that we take this negative 5 and that 3i, we switch the sign from a negative, in this case, to a positive, and we multiply that number over itself. So negative 5 plus 3i. Again, I'm using the shortcut here, which means ignore the signs, ignore the signs, ignore the I. I'm purely doing 5 squared plus 3 squared. I'll even show my shortcut this time better. I'm doing 5 squared plus 3 squared. And that will always give me a 25 plus 9. That'll give me 34 in this case. All right. The unfortunate bit of this shortcut is it doesn't work on the numerator, which means I have to do this one manually. All right. Negative 9 times a negative 5 is a positive 45. A negative 9 times a positive 3i is a negative 27i. I'm going to need some more room, so let's go ahead and move these over a little bit, extend our division line, messily, but it works. I'm doing a positive 10i times a negative 5, which is a negative 50i, and then finally a positive 10i times this positive 3 is a positive 7 or positive 30i squared. I'm noticing that I have an I squared term, which is going to turn into a negative 1. And let's see what we have. I have a negative 1 times a 30, which is negative 30. Negative 30 plus 45 is a positive 15. Next, I have my imaginary terms. These are both the same signs, so they go in the same direction. I'm adding a 27 with a 50 to get a total of 77i in the negative direction, so minus 77i. I'm taking a look to see if any of these have like denominator or like terms, like can I divide them by 3? Do they have like factors? That's what I'm looking for. Factors are 3 and 5, factors are 7 and 11, factors are 17 and 2. None of these share factors, which means I cannot reduce, and that is my final answer, which I will then box. Just as a reminder, you could also multiply the numerator and denominator by negative 1. If you did that, you would get a negative 15 plus 77i all over a negative 34. This is also a valid solution. All right, and I'm just checking my work. 15 minus 77i over 34. That was the answer that they got. They got my first answer. That concludes our practice test for Algebra 2. It's practice test 6. Thanks for watching.